Bismillahirrahmanirrahim. The power efficiency of amplitude modulation refer to the proportion of the total transmitted power that is effectively utilized in conveying the actual information signal or message compared to the total transmitted power including the carrier. In standard AM, most of the transmitted power is concentrated in carrier, which does not carry any information, and a smaller fraction is allocated to the sideband where the information resides. The efficiency is determined by the modulation index, which is the ratio of modulating signal amplitude to the carrier signal amplitude. Maximum power efficiency in AM is achieved at the modulation index of 1, corresponding to the condition where the sideband power is maximized without the causing overmodulation. Under these conditions, the power efficiency of AM reaches a theoretical maximum of 33.33%, with the remaining power consumed by the carrier. This inherent limitation make AM less power efficient compared to the other modulating techniques such as single sideband or frequency modulation. In this unit 15, we will discuss the detail and drive the equation for the power efficiency of amplitude modulation. Now we discuss how an amplitude modulated wave is formed and why its total power increases after modulation. In AM, the modulated wave is a combination of three components: the carrier wave, the lower sideband, and upper sideband. The lower sideband is represented by LSB and upper sideband represented by USB. The LSB and USB are generated as a result of modulation process which involves combining the carrier wave with the message signal. These sidebands represent the frequencies that carries the actual information content of the signal. Because the sideband add additional energy to the waveform, the total power of the modulated wave becomes greater than the power of the original carrier wave. The amplitude at the sideband is proportional to the modulation index, which quantifies the extent to which the carrier wave is modulated by the message. Therefore, the modulation index directly influences the total power of the modulated wave. Higher modulation indices result in a stronger sideband and greater total power, while lower modulation indices result in weaker sideband and less additional power. Now we see that here this the AM signal can be represented by AC 1 plus m cos omega cos pi fmt and multiplied by cos pi 2 pi fct, where fm is a modulating signal frequency, linear frequency, and fc is a carrier frequency. Now we describe the composition and power characteristic of amplitude modulated wave. Here the detailed explanation. Composition of the modulated wave, where the carrier wave is modulating by the message or modulating signal. The resulting AM consists of three components: carrier wave, lower sideband, and upper sideband here. So upper sideband, the carrier power can be written as the AC square over 2, where AC is the amplitude of the carrier wave. Similarly, the total power of AM is equal to PC multiplied by 1 plus m squared divided by 2, where the sideband power P sideband is equal to PC multiplied by m squared by 2. Now we have all three information. We know the carrier power and total amplitude power and sideband power. It will help to determine the power efficiency in the next slide. Now the power efficiency is defined as the ratio of PSB over PAM. power of the sideband by the modulated signal power. In previous slide, we determined that PSB is equal to simple PC multiplied by m square by 2, where PC is the power of the carrier signal, and modulated signal is PC bracket start 1 plus m square by 2. So PC is common, so it is cancelled out, and power efficiency can be determined by the m square by 2 divided by 1 plus m square by 2. It is a very simple and fundamental equation to determine the power efficiency of the amplitude modulated signal. Now we are interested to determine the maximum power efficiency of the amplitude. You know that modulation index is value from 0 to 1 and it can be greater than 1. But generally we do not prefer above than 1 because after 1 it is distortion of the signal will be started. So practically we can say that for effective communication the maximum value of the amp is equal to 1. So when we incorporate these values, so our power efficiency become half square divided by 1 plus half square. So now we have power efficiency is equal to zero point 0.5 divided by 1.5 and it is equal to the 1 by 3. It is 33.33%. The maximum power efficiency of AM system is approximately 33.33%. It is not possible for a effective communication. We can have a higher power than efficiency. This is means that ideal AM signal with 100% modulation, only one third of the total power transmitted power is used to carry the signal. This is the very serious drawbacks of amplitude modulation. In a traditional amplitude double sideband system, the carrier signal itself does not convey any information. Instead, the information is carried within the sideband. This system has following disadvantage. The carrier signal accounts for two-thirds or more than two-thirds of the total transmitted power. Both sideband carry identical information, making it redundant to transmit both with double the bandwidth usage compared to the single sideband system. Conventional amplitude modulation is highly inefficient in terms of both power and bandwidth utilization.